There is a certain kind of question that only appears when the world grows quiet, when the listener, half awake and half drifting, suddenly wonders why so much of the ocean's earliest history seems to be missing, or blurred, or rearranged. It's strange how the deeper one looks into prehistoric seas, the more the story slips away from the familiar path, as though someone long ago erased parts of the tale and forgot to smooth the pages. And as the mind settles into this quiet wondering, this drifting between curiosity and sleep, there's one small thing to do. So before you get too comfortable, take a moment to like the video and subscribe, but only if you really like what I'm doing here. And if you're listening tonight, tell me where you are and what time it is there, as you sink with me into the first layer of the ancient sea. The contradiction begins simply. Fossils near the old shoreline seem to tell a straightforward story of early life, one that follows the accepted sequence of growth, adaptation, and change. But the moment the gaze shifts deeper, when the layers of sediment mark not shallow waves but cold pressurized darkness, something begins to feel out of place. There are creatures that appear without warning, forms far more elaborate than their supposed ancestors, bodies shaped by forces no one fully understands. It is here, in this contrast between the simple and the inexplicably complex, that the first questions about prehistoric oceans quietly begin to grow. Paleontologists have long noted that some early marine species, especially those from deeper habitats, seem to carry traits that shouldn't appear until much later. Their anatomy suggests an environment both ancient and highly specialized, as if evolution ran ahead of schedule. But when the sediment around these fossils is dated, when isotopes are measured and cross-checked, the results drift into uncertainty. Sometimes the layers don't align with the story the organism tells. Sometimes the organism doesn't align with the story the layers tell. The deeper the site, the more the dissonance grows. This is not the kind of contradiction that gets loudly discussed in textbooks. It's a quieter kind, noticed in passing by researchers cataloging deep ocean specimens from the Cambrian or Ordovician periods. They write about it in footnotes, brief comments on unexpected complexity, poorly constrained depth ranges, or unusual ecological placement. But when these scattered remarks are read together, when one traces them from one study to another, a subtle shadow forms, a sense that something happened in the depths that does not match the narrative of life rising from simplicity into complexity. Instead, it hints at complexity appearing early, disappearing, then returning again from places we cannot fully access. The deep sea is notoriously stingy with its fossils. Pressurized darkness does not easily preserve delicate forms, and many layers have been subducted or warped beyond recognition. And yet, in rare cases, such as certain deep Cambrian deposits in China, or enigmatic Ordovician strata off the coast of Morocco, creatures emerge that are too refined for their geological moment. They have articulated limbs, sophisticated sensory organs, even early signs of light detection structures that imply the presence of bioluminescent environments. How could this happen so early? And why only in deeper contexts? One of the most whispered about examples comes from anomalocaridids, ancient predators that dominated Cambrian seas. Some species appear suddenly in deep water environments with physical adaptations far beyond their shallow water relatives. By standard evolutionary timelines, such traits should have taken millions of years to develop. Yet the fossils suggest otherwise. They suggest a leap, uncomfortable, untraceable, but unmistakable. When researchers attempt to reconstruct their lineage, they find empty spaces rather than a clear chain. The ancestors seem missing. The transitions seem absent. The story feels incomplete, This pattern repeats itself across multiple eras. In some Ordovician sites, deep-water trilobites show advanced eye structures earlier than their shallow water counterparts. Some Devonian fish found in deeper deposits display unusual jaw morphologies that appear thousands of years earlier than expected. Each case on its own is a curiosity. Together, they form a quiet chorus, asking whether the ocean's deepest regions develop their own timeline, one not easily reconciled with the surface world. Modern expeditions reflect the same uneasy feeling. When submersibles descend into Hadal trenches or explore hydrothermal vent fields, they often discover new species with ancient genetic signatures. Some lineages appear so old, so unchanged, that they seem like echoes of earlier ages, preserved in the isolation of depth. It's almost as if the deep sea is a library of forgotten drafts, chapters the surface world lost or rewrote. But the question is why? Why would the deepest places preserve what the upper layers erased? Or more unsettling, could something have forced the rewriting? There are, of course, scientific explanations. Some propose that deep-sea environments provide stability during global catastrophes, shielding lineages from extinction. Others suggest that ancient chemical conditions, higher pressure, lower oxygen, or volcanic activity could have accelerated certain evolutionary pathways in deep habitats. These are reasonable theories, grounded in geology and biology. Yet even within these frameworks, the puzzle remains. Why do some complex deep-water species appear before their shallow water equivalents? Why are their transitional forms missing? Why do they vanish again as abruptly as they arrived? The deeper one looks, the more the evidence feels like fragments of a broken timeline, pieces of an oceanic history that once existed, but was later disturbed, reshaped, or overwritten. It brings to mind the concept of disappearing ancestors, found in certain genomic studies, where ancient species leave traces of DNA with no known origin species to explain them. In the oceanic fossil record, the effect is even more tangible. Stone layers where complexity blooms too early, fades too quickly, and leaves more questions than answers. None of this is presented as a conspiracy or a hidden agenda. It is simply the nature of the abyss. Pressure, darkness, time, and silence conspiring to obscure what once lived. Maybe nothing unusual happened. Maybe the ocean's deepest layers simply operate with rules we still don't understand. But there is a lingering unease in the way these early organisms appear and vanish. A feeling that something is missing from the story, or perhaps deliberately lost. As the sediments grow darker and the pressure rises in the imagination, one begins to sense that the deeper layers of the prehistoric ocean are not just physically remote, they are historically remote as well. They hold traces of life that seem too advanced for their era, too isolated, too abruptly terminated. And just as the listener feels the edges of that realization, something else emerges. A small, lingering question about what lies beneath those contradictions. Whether they point toward a natural gap, an eroded history, or the first sign of a rupture whose cause has not yet been named, somewhere between the fading outline of the first contradiction and the quiet drift of thought that follows it, another uncertainty rises. One that has lingered in scientific literature for over a century, but rarely draws public attention. When researchers map the biodiversity of prehistoric oceans, they keep stumbling upon an odd pattern. Entire ecosystems appear suddenly, flourish briefly, and disappear with almost no trace of how they began or where they went. The more carefully one looks at the transitions between shallow and deep zones during the Ordovician and Silurian, the more the ocean begins to feel like a place that periodically resets itself. leaving only fragments behind as if someone rearranged the pieces while the rest of the board slipped quietly into darkness. This is not merely a poetic impression. Many scientists have remarked on the discontinuities found in early Paleozoic marine life, moments where complexity appears too abruptly, spreading across the ocean floor with exuberance and then fading just as quickly. The so-called Great Ordovician Biodiversification Event, one of the most dramatic expansions of marine life, erupted into existence almost as suddenly as the Cambrian explosion before it. But unlike the Cambrian, which left behind iconic fossil sites, the Ordovician world left fewer detailed records. It is like walking into a room where you can still sense that a celebration happened earlier. But all the guests are gone. The candles have been extinguished, and only scattered objects remain on the floor. You can infer the event, but you cannot witness it. Even more puzzling are the deeper water assemblages from these periods. Many units show bursts of unusual organisms, graptolites branching into unfamiliar forms, deep water trilobites developing elaborate spines or sensory structures, and soft-bodied creatures appearing in environments normally unfriendly to preservation. Yet their origins are obscured. They emerge not from a gradual buildup of complexity, but from what seems like an empty stage. Their ancestors are faint or missing, and the sediment that should contain the earlier steps is often disturbed, thinned, or absent. Some geologists attribute these inconsistencies to tectonics. The Ordovician and Silurian eras were times of shifting continents, rising mountain belts, and sinking basins. The seafloor was in motion, and deep water sediments might have been destroyed or buried beyond reach. But even this explanation feels partial, because the discontinuity is not only in the rocks, it is also in the biology. Genetic studies of surviving lineages suggest that some groups expanded far earlier than their fossils indicate. Others show signs of bottlenecks or sudden diversification that do not correspond neatly to environmental shifts. It is as if parts of the evolutionary record were overwritten, not through catastrophe but through a kind of quiet erasure. In certain places, the silence is almost unnerving. Take the ancient seas around what is now the Yangtze platform. There, deep marine strata reveal organisms whose ecological roles do not match the expected structure of Ordovician ecosystems. Predators appear in layers where prey species are scarce. Soft-bodied organisms show adaptations that imply long evolutionary histories in environments for which we have almost no fossil evidence. It is not that these creatures do not belong. They clearly evolved from something. It is that the something has vanished. The Silurian period, often overshadowed by the Cambrian and Devonian, deepens the mystery. Its reefs blossomed with spectacular diversity, including early corals and stromatoporoids. Yet some reef-building organisms appear in the fossil record fully formed, without a gradual development of intermediate shapes. Their deeper water relatives, adapted to cold, low-light conditions, materialize abruptly, as though carried from an older world. When researchers attempt to trace their lineages backward, they find themselves stepping into geological fog. At a certain point, the trail simply dissolves. Some propose a simple explanation: fossilization bias. The deeper the water, the harder it is for life to be preserved. But the question persists in the spaces between the conclusions. If bias alone were responsible, one would expect a consistent lack of fossils. Instead, we find bursts, short windows where deep-sea life reveals itself clearly before fading again. These windows are scattered across different time periods and different continents, but they share one uncomfortable trait. They rarely show the gradual buildup that evolutionary models predict. They feel more like brief flickers of revelation. Then, there is the issue of the Lazarus taxa. species that disappear from the fossil record for millions of years, only to reappear unexpectedly. Many of these vanishings occur in deep water groups, where entire families seem to fall silent during periods of environmental change. Yet when they return, they often do so without significant alteration, as if they had been quietly living elsewhere, hidden from sediment and time. Scientists have documented this pattern through multiple extinction events, most notably the late Ordovician mass extinction, where deep-sea communities recovered in ways that contradict the typical model of ecological collapse. Some lineages seem to have waited out the crisis in places we still cannot pinpoint. If the ocean surface represents a story we can read, the deep sea feels like a palimpsest, an ancient manuscript overwritten again and again, with faint lines of earlier writing still detectable beneath the newer script. Each attempt to decipher it reveals both presence and absence, clarity and erasure. One researcher once described the Silurian deep sea as a memory half-washed clean, and though the phrase was meant metaphorically, it captures the quiet unease that accompanies every analysis of these eras. Take, for example, the study of conodonts, microfossils whose tooth-like elements reveal much about ancient marine environments. Conodonts thrived in a range of depths, yet deep-water species often show abrupt shifts in morphology unrelated to environmental proxies like oxygen or temperature. Their changes seem untethered to the surrounding context, as though responding to pressures not visible in the geological record. These are not conclusions scientists can publish without caution, but they linger in discussions, in conference corridors, in the footnotes that careful readers never skip. Even the sediments themselves seem to cooperate with the sense of incompleteness. When core samples are taken from areas that were once deep Paleozoic basins, the layers sometimes appear strangely compressed or disturbed, as if something passed through them and unsettled the record. In other places, entire segments are missing, not eroded, not subducted, but simply absent. Geologists refer to these as hiatuses, but the term explains only the fact, not its cause. This growing pattern, ecosystems blooming without visible precursors, deep-sea life evolving along paths that resist reconstruction, genetic timelines asking questions that rocks cannot answer, creates an impression more philosophical than scientific. It hints at the possibility that the ocean once held worlds within worlds, layers of life moving in rhythms we have not yet learned to perceive. Perhaps some chapters were lost through natural processes. Perhaps others were never recorded at all. But as the listener drifts further into this unfolding mystery, there remains one detail that refuses to settle: the sense of deliberate absence. Not the absence caused by erosion or subduction, but the kind that feels intentional, like pages removed from a book long before anyone alive today ever held it. Whether that feeling is justified or merely a byproduct of curiosity is uncertain. Yet it lingers at the edge of thought, subtle and persistent, inviting the mind to descend another layer deeper, where a new fragment awaits. Not an answer, but another quiet question, half lit by the dim glow of a world too old to speak clearly. There is a moment, somewhere after the vanished ecosystems and the uneasy silence they leave behind, when the listener begins to sense that the ocean's deepest layers might not simply be missing chapters. They may belong to a different book entirely. The mid-Paleozoic world, particularly the era that bridges the Silurian into the Devonian, contains a kind of darkness that is not just physical, but historical. At these depths, life behaves differently. It surfaces in the record abruptly, retreats without warning, and reappears thousands or millions of years later carrying traits that seem unanchored from the shallow water narrative. It is here, in this abyssal quiet, that another circuit of the mystery begins. The mid-Paleozoic deep sea has always presented an uncomfortable puzzle. While shallow waters show predictable patterns of evolutionary progression, corals building reefs, fish diversifying, arthropods experimenting with new limbs and senses, the deep basins tell a different story. Fossils from these regions, when they appear at all, often represent organisms that do not match their time frame. Their genetic lineages, where measurable, suggest ancient origins that precede the strata they are found in. Their morphology sometimes implies relationships to species not yet evolved in the layers above. These contradictions are not loud. They whisper from the sediment, faint but persistent. One of the most intriguing pieces of this puzzle is found in deep water brachiopods and trilobites of the mid-Paleozoic. Many species appear in geographically distant basins with nearly identical forms, as if evolution elsewhere paused while the deep sea continued its own quiet experiment. Some trilobites show eye reductions, sensory adaptations, or spines suited for pitch-black environments. Yet these features appear before similar adaptations in their shallow water relatives. This reverses the expected timeline. It suggests that the deep, rather than lagging behind, was advancing in ways we do not fully understand. Some researchers propose that these lineages represent deep-sea refugia, isolated pockets where life persisted during environmental instability. But even this explanation falters when examined closely. If the deep sea sheltered ancient lineages, we should see earlier evidence of their presence. Yet in many cases, the geological layers that ought to contain their ancestors are missing or altered in ways that make them unreadable. It's as though the story begins mid-sentence with the earlier lines erased or sealed away. Geochemical studies deepen the mystery. When scientists analyze carbon and oxygen isotopes from mid-Paleozoic deep-sea sediments, they find unusual fluctuations that do not correspond neatly to surface events. Some records indicate anoxic conditions when surface waters were stable. Others show chemical shifts that predate known extinction events. In a few rare cases, isotopic signatures imply biological activity at depths during periods when parts of the surface world appear nearly lifeless. It is difficult not to wonder what kinds of organisms could thrive in such darkness, and why they left so little trace of themselves in the fossil record. Then there are the methane seeps, ancient hydrocarbon-laden environments that once dotted the deep ocean. These sites supported unique communities of organisms, tube worms, crustaceans, bivalves adapted to chemical nourishment rather than sunlight. Modern analogues exist near present-day hydrothermal vents, but their Paleozoic predecessors appear and disappear abruptly. Some deposits show evidence of thriving ecosystems that lasted for millions of years, yet the transition into and out of these habitats is hidden. The organisms seem to materialize, live, and vanish without leaving transitional fossils behind. This pattern repeats across different basins, as though each site participated in a phenomenon not preserved in traditional strata. One of the most debated examples involves Devonian fish found at surprisingly great depths. Some species possess advanced jaw structures and sensory organs that appear too early compared to shallower relatives. Their placement in the timeline forces a series of uncomfortable questions. Did these lineages evolve in the deep and later migrate upward? If so, why do their ancestors remain invisible? Or did they develop independently in multiple isolated basins, resulting in convergences so precise they seem improbable? These are questions rarely asked in mainstream discussions, but they linger beneath the surface of scientific papers, their edges softened by cautious phrasing. Even the sedimentary patterns contribute to the unease. Deep-sea cores from mid-Paleozoic basins sometimes show fine layering interrupted by chaotic deposits, flows of disturbed material that seem to originate from sudden collapses or unknown events. Some layers are oddly thinned, others are missing entirely. Though tectonic explanations exist, they do not always fit the scale or distribution of these disturbances. In a few cases, thin layers of volcanic ash appear hundreds of meters deeper than expected, hinting at unusual processes of deposition or later alteration. The deeper one studies these sequences, the more the sense of an underlying rupture begins to stir. The deep time abyss also contains survivors, organisms that endured extinction events in ways that defy predictive models. During the late Devonian crisis, when reefs collapsed and shallow ecosystems faltered, certain deep-water lineages persisted with little disruption. Others disappeared before the extinction began, as though withdrawing in advance. Some of these groups later reappeared in the early Carboniferous, unchanged, as if they had been sheltered by environments we have not yet discovered or cannot access. This cyclical pattern of disappearance and return does not resemble traditional evolutionary pathways. It resembles something more fragmented, like glimpses into rooms connected by corridors we cannot map. Genetic bottlenecks offer another clue. Modern descendants of deep-sea lineages often show reduced genetic diversity, implying ancient population crashes followed by isolated recoveries. Yet these timelines do not always match known surface events. Some bottlenecks seem to correspond to disturbances unrecorded in shallow ecosystems. Others suggest that deep-sea conditions fluctuated for reasons not reflected in surface climate proxies. If the deep ocean experienced events invisible to surface environments, what could have caused them? A natural cycle? Oceanic chemistry? Something more abrupt? When all of these fragments are placed side by side, the sudden appearances, the missing transitions, the isotopic anomalies, the survivors that emerge from nowhere, a subtle but persistent impression forms. It is not that the deep sea hides answers. It is that it hides the questions themselves. The shadows in the record do not just obscure facts. They obscure the shape of the mystery. And as the listener drifts through this tangle of forgotten basins and unaligned timelines, a final detail emerges to unsettle the stillness. In several deep marine studies, there exists a phenomenon researchers rarely comment on directly: signals of biological activity that appear during intervals of global silence, as though life in the abyss followed a rhythm out of sync with the rest of the planet. These signals are faint, contested, and easy to overlook. But for those who linger on them, they raise a quiet, haunting question. One that does not answer, only deepens the descent. What if the deep ocean once moved to a different timeline? And what if some part of that timeline remains, waiting in the darkness where the record grows thin? If the previous threads linger in the listener's thoughts, like half-formed shapes in dim water, then the next layer descends into something stranger, a place where the ocean's history does not simply blur, but fractures. The deeper one moves into the Devonian and toward the boundaries that separate it from the worlds before and after. The more the sediment begins to behave like memory under strain. Whole chapters thin into whisper-like impressions. Others swell into compressed, darkened pages. And then there are the stretches where the rock itself feels absent, as if time folded inward and left only a ghost layer behind. Geologists call these places unconformities, gaps, hiatuses, missing segments of the geological story. Some are caused by erosion, some by shifts in sea level, some by tectonic forces rising from within the crust. Yet in deep marine contexts, especially those marking the transitions into or out of the Devonian, many of these gaps refuse to behave like ordinary erosion. The layers are not worn away but squeezed, distorted, or abruptly interrupted, as if something disrupted the balance of sedimentation itself. Among these enigmatic boundaries, the Hungenberg event at the end of the Devonian is one of the most haunting. It is marked by black shales, dark, organic-rich sediments that speak of oceans starved of oxygen. What unsettles researchers is not the presence of anoxia. Such crises are known in Earth's history. What unsettles them is the way the black shale layer appears across distant continents with eerie uniformity, as though a single quiet catastrophe touched every deep basin at once. In places where thick sediment should record the slow decline of marine life, the layers collapse into a thin, shadow-like streak. And in the strata directly below this line, deep water fossils begin to fade, not gradually but with a suddenness that feels almost deliberate. Some species vanish before the anoxia should have reached their habitats. Others appear to persist in narrow pockets where the chemistry suggests survival was impossible. Researchers write about these anomalies in careful, measured terms, but the effect remains. The deep ocean around the Devonian Carboniferous boundary behaves as if its history has been smoothed over, leaving only the residue of an event too evenly distributed to be explained by localized changes. Then there are the ghost layers, sedimentary intervals that exist physically but resist interpretation. In some regions, these layers are laminated and undisturbed, suggesting calm, stable deposition. Yet their chemical signatures contradict stability. They show rapid fluctuations in carbon and sulfur isotopes, implying sudden shifts in ocean circulation. A few sites reveal spikes in mercury levels, hinting at volcanic activity. Others contain microtectites, tiny spherical grains associated with impacts. But none of these signals align neatly. It is as if multiple stories were written into the same thin layer, overlapping like voices speaking from different rooms. One of the most quietly debated examples occurs in the deep water sections of what is now Western Australia. There, sediments from the late Devonian show signs of abrupt environmental stress, trace metals associated with hydrothermal disruptions, rare earth element anomalies, shifts in redox conditions. Yet the fossils within them suggest periods of biological calm. Some lineages appear unaffected, others vanish inexplicably, and still others reappear above the boundary unchanged. The conflict between the geochemistry and the paleobiology feels like a riddle. The rocks say crisis, the organisms say continuity, but the layers in between say nothing at all. A similar tension emerges in Europe's Rhenish Massif, where deep marine cores show an odd pattern in the very moments before the Hungenberg horizon. The sediment grows progressively finer, almost powder-like, then suddenly thickens into a dark streak. Within this streak, conodont elements are present, but distorted, compressed, fractured, sometimes aligned in single directions, as if rearranged after deposition. Some researchers argue for turbidity currents or submarine landslides. Others point out that the directionality does not match known patterns of underwater flow. Whatever caused this alignment left behind an impression of movement without a clear source. Across these distant regions, a shared question emerges. Why do deep water boundaries from this era feel both intensely recorded and strangely erased? Why do the rocks capture hints of upheaval, but lose the details of its unfolding? And why do the organisms seem to sense the crisis before it arrives, withdrawing from the fossil record as though anticipating a silence that has not yet begun? When scientists attempt to reconstruct the ocean circulation of the late Devonian, they confront another layer of the puzzle. Models suggest that deep waters became unstable, prone to sudden overturn events. Such events could drag oxygen-poor water to the surface or pull surface organisms into the abyss. But these models rely on assumptions. They cannot explain the precision with which certain species disappear at the same stratigraphic moment across continents. Nor can they explain why some basins record prolonged anoxia, while others show rapid recovery. Every attempt to fit the pieces together leaves a fragment unaccounted for. What makes the Hungenberg Horizon so unsettling is not merely what it contains: black shale, rare fossils, signs of chemical stress, but what it refuses to contain. The transitional layers that should reveal the approach of catastrophe are often missing or compressed. The intervals that should capture life's return are faint or incomplete. The story of the boundary feels like a film that suddenly jumps frames, leaving the viewer aware of an absence but unable to name it. Some scientists have suggested that the deep ocean experienced multiple discrete disturbances during this time: chemical pulses, temperature shocks, overturns, each too brief to leave a full record, but impactful enough to disrupt ecosystems. Others argue for a single global trigger: a massive volcanic episode, an impact, or rapid climatic change. But even these possibilities do not fully align with the geological pattern of compression, thinning, and selective erasure. It is this selective quality that invites deeper reflection. Why do the layers preserve the onset of anoxia so clearly, yet obscure the events leading up to it? Why are some deep marine fossils preserved with exquisite detail, while the layers immediately below them are marred or missing? Why does the ocean reveal its darkest moments so faithfully, but whisper so little about what came before? As these questions accumulate, the listener may begin to sense a subtler theme rising beneath the scientific data. The idea that the deep sea does not simply record history, it chooses what to remember. Whether this choosing is geological, chemical, or something more abstract is not the point. What matters is the impression it leaves, the feeling that history in the abyss is not a continuous scroll, but a tapestry woven with intentional gaps. And somewhere within those gaps lies the faint impression of a rupture. Not a violent one, perhaps, but a quiet, structural break in the way the ocean preserved its own past. A boundary where something changed in the rules of memory. A boundary that suggests the deepest layers of Earth once witnessed an event, or a sequence of events, that the shallower world never saw. What that event was remains hidden behind the ghost layers, waiting in the darkness where the sediment refuses to speak plainly. And as one listens closely to the silence pressing from those depths, the next question begins to form, subtle and unresolved, urging the descent to continue. By the time the listener reaches this point in the descent, the surface world has grown distant, like a dim memory fading behind layers of pressure and time. And in this deep, quiet place beneath the ghost horizons, another pattern rises, not from the rocks themselves, but from the creatures that once navigated the darkness. If the boundaries and gaps hinted at a fracture in the ocean's history, the organisms found below those breaks seem to carry that fracture in their bodies. They appear suddenly, shaped for a world without light, built as though they belong to the darkness from the beginning. And yet they often emerge in the geological record before their shallow water counterparts evolve the same traits. It is as if the deep sea wrote a different script, one that the surface only learned to imitate later. These creatures, some familiar, some unnervingly foreign, form one of the ocean's most haunting mysteries. They are not defined by monstrous size or dramatic appearance. It is their timing, their placement, that unsettles the rhythm of Earth's story. The deeper one looks, the more the earliest signs of darkness-adapted life seem to precede the conditions that should have shaped them. Bioluminescence, for example, is a trait so ancient and widespread that its origins remain one of evolutionary biology's lingering questions. Modern deep-sea organisms rely on it for communication, predation, camouflage, and survival. But the compounds associated with bioluminescence, luciferins and their related enzymes, appear in lineages separated by enormous evolutionary distances. Molecular studies indicate that these systems may have arisen earlier than the ecosystems where they are most useful. And in several fossil-bearing deposits from the Cambrian and Ordovician, soft-bodied organisms show structures that resemble primitive light-producing organs. This suggests that darkness-adapted strategies existed long before the deep ocean reached the conditions known today. Then there are the anomalocaridids, whose deep-water forms reappear millions of years after their shallow relatives fade from the record. Their resurrected presence in these depths, unmistakably advanced, uniquely adapted, strains the narrative of linear evolution. How could a lineage vanish from view, only to surface again in environments it supposedly did not inhabit earlier? And why do the later deep-water forms appear more specialized than the earlier shallow-water ones? A similar tension surrounds early-jawed fish of the Devonian. Some specimens found in deep-water deposits exhibit features years ahead of their shallow-water relatives: complex sensory canals, reinforced fin structures, or expanded lateral line systems built for navigating low-light environments. In several regions, paleontologists have found deep-water species whose bones preserve evidence of pressure-specific adaptations long before comparable structures appear near the shore. These organisms were not merely surviving in darkness. They were thriving, evolving, and refining themselves in a world that should have been hostile. And then there are the enigmatic eurypterids, sea scorpions, that appear in both shallow lagoons and deeper basins. But the deepest forms often possess traits that are counterintuitive: enhanced appendages, thicker exoskeletons, and ornamentation that suggests communication or display, though such signals would be useless in darkness. Some researchers argue these features evolved for tactile or chemical interactions. Others suggest they are remnants of earlier, more illuminated habitats. Yet their sudden emergence in deep-water contexts makes both explanations feel incomplete. The most enigmatic, however, may be the early cephalopods. While many associate ancient cephalopods with shallow waters, evidence has emerged of deep-water nautiloids and early ammonoid relatives possessing buoyancy structures far more sophisticated than expected for their era. Their shells show internal complexities, cambered chambers, sipuncle modifications that imply pressure adaptation. These organisms did not evolve into the deep gradually. They arrived there prepared. This pattern, that deep water traits often appear first, with surface analogs following later, troubles researchers who expect evolutionary change to begin where sunlight and energy are abundant. The deep ocean is not where complexity should emerge first. And yet the fossil record, incomplete but insistent, continues to whisper that something different happened. Some scientists propose that these deep water lineages represent remnants of earlier worlds, survivors of old ecosystems that retreated into darkness during environmental upheavals. But this idea raises its own questions. If these organisms came from older ecosystems, where are the fossils of those ancestors? Why are their origins invisible while their later forms are clear? And why do so many of these lineages appear in multiple distant basins at nearly the same moment, as though emerging from hidden refuges simultaneously? Others suggest that the chemistry of the early oceans, rich in metals, sulfides, and thermal gradients, may have spurred rapid specialization in deep environments. Hydrothermal vents, methane seeps, and volcanic arcs could have created microhabitats where evolution advanced at accelerated rates. But even this hypothesis cannot fully explain the absence of gradual transitions, the jumps in morphology, or the repeated pattern of deep first evolution. The more evidence one gathers, the more a subtle impression emerges. The deep ocean does not merely hold the remnants of past life. It holds remnants that feel older than their strata allow. It is as if the deep preserves echoes from an earlier version of the world, one that left almost nothing behind except organisms strangely prepared for the conditions they would later inhabit. In certain deep Cambrian deposits in British Columbia and China, researchers have found small, soft-bodied forms with structures so anomalous they resist classification. Some possess elongated sensory filaments, others have eye stalks designed for low-light detection, and still others show unusual chemical signatures preserved in the surrounding sediment, hinting at environments rich in hydrogen sulfide or methane. These organisms were not experiments. They were specialists. Their existence suggests ecosystems functioning at depth long before the ocean's chemistry reached the stability required for such complexity. What makes the puzzle more haunting is the behavior of these lineages after they first appear. Many vanish quietly, leaving no descendants. Others retreat to greater depths, becoming rarer with time. A few survive extinction events, appearing again millions of years later with minimal change. Their evolutionary trajectories do not arc smoothly or predictably. They flicker, an imprint here, an absence there, like a lantern carried through darkness, visible only when the holder passes briefly into the light. And as one contemplates these creatures, so exquisitely built for a world without illumination, a quiet question forms beneath the scientific details. If these organisms were shaped for darkness before the conditions of that darkness were fully established, what does that imply about the history we think we know? Did these traits evolve in environments we have not yet found? Or were there earlier, deeper oceans, worlds erased by subduction, pressure, and time, whose inhabitants re-emerged only when conditions aligned again? The listener may not find an answer waiting here. The deep sea rarely provides answers. It offers fragments, each shaped by pressure and obscurity. Yet in studying these fragments, creatures adapted before their time, appearing and vanishing at the edges of visibility, one feels the contours of a larger mystery stirring just beyond reach. And somewhere within that stirring lies the faint sense that these organisms were not only shaped by the darkness, they carried the memory of an older darkness, one that predates the layers we can see, and hints at something submerged even deeper, waiting beneath the next descent. As the descent continues and the listener drifts deeper into this submerged corridor of vanished forms and premature adaptations, another dimension of the mystery rises, not from the creatures themselves, but from the world that surrounded them. For every organism that seems misplaced in time, there is an environmental shift that feels equally out of alignment. The prehistoric oceans did not merely host life. They shaped it through cycles of catastrophe and quiet, upheaval and calm. Yet the records of these cycles do not always match the patterns preserved in surface sediments. In many cases, the deep ocean appears to have endured disturbances that the shallow world barely noticed, and at other times, it remained strangely unscathed while surface ecosystems collapsed. The deeper one examines these inconsistencies, the more the ocean begins to resemble a world divided, one part visible to history, the other hidden beneath its own chemistry and pressure. The Devonian and early Carboniferous periods, often described as eras of instability, reveal some of the most striking contradictions. While volcanic activity, sea level fluctuations, and climatic swings undoubtedly shaped marine ecosystems, the deep ocean's response often appears asynchronous. In certain cores from ancient basins near what is now northern Europe, geochemists have recorded abrupt changes in osmium and mercury levels, signals typically associated with volcanic eruptions or hydrothermal surges. Yet the shallow water fossils from the same periods show no sign of corresponding trauma. It is as though eruptions unfolded in darkness, their impacts diffused or absorbed before reaching the light-filled world above. Conversely, when global events such as the Kellwasser extinctions devastated reef systems and surface organisms, deep water communities in some regions remained unexpectedly stable. Trilobites and conodonts inhabiting the abyss exhibit little evidence of disruption during these surface crises. In other regions, though, deep-sea species vanished before shallow water decline began, as if responding to changes invisible in the surface record. The ocean seems to pulse with layered timelines, one visible, one concealed, each reacting to forces the other cannot detect. Some of these forces may have been internal to the ocean itself. There are hints, scattered through various scientific papers, that ancient overturn events, moments when cold, oxygen-poor water rose rapidly from the abyss, occurred far more frequently than once believed. Such upwellings of the dead would have drastically reshaped marine chemistry, triggering collapses in surface ecosystems even without external triggers. Yet, at the same time, deep water organisms accustomed to low oxygen conditions might have remained unaffected, sheltered by their own adaptations. It would explain the puzzling contrast between shallow water die-offs and deep water continuity. But this hypothesis raises its own uncomfortable questions. If overturn events were so frequent, why do they leave such uneven geological signatures? Why do some basins show abrupt shifts in redox conditions while others retain stability? Other studies suggest that methane eruptions, sudden releases of methane hydrates from the seafloor, may have contributed to these environmental disturbances. These eruptions can trigger rapid cooling or warming, alter carbon isotopes, and create toxic conditions in certain depths. There are Devonian and Carboniferous sediments that show these exact fingerprints, sudden negative carbon isotope excursions, spikes in barium and strontium, and the presence of unusual biomarkers associated with methane oxidizing microbes. But these signals appear sporadically, often without the accompanying fossil evidence one would expect. It leads some researchers to speculate about isolated deep-sea events, massive in scale but confined to particular basins, never fully reaching the surface. What makes these theories so haunting is not just their complexity, but their implications. If the deep ocean experienced its own independent catastrophes, events that left only faint traces in surface strata, then the history of life as we know it may be biased toward the shallow regions that preserved their stories. The abyss may have undergone transformations, extinctions, and recoveries that are nearly invisible, except for a handful of organisms that flicker into the fossil record, like brief, fragile lanterns in the dark. Even more unsettling are the chemical signatures found in certain mid-ocean ridge and back arc basin sediments. At times when shallow seas exhibit stable conditions, deep water deposits show anomalies indicative of intense hydrothermal activity, elevated iron, manganese, or rare earth elements that suggest rapid fluctuations in temperature and chemistry. These signals imply that volcanic or tectonic forces beneath the ocean may have surged unpredictably, creating heat pulses that reshaped deep ecosystems before dissipating. But the timing of these pulses often conflicts with known tectonic events. They seem to occur when the lithosphere above should have been quiet. One study analyzing chromium isotopes in deep marine black shales even proposes that large regions of the ocean became intermittently stratified, divided into layers that prevented the circulation of oxygen. Such stratification could have trapped entire ecosystems below chemical barriers, preserving them for long periods before collapsing suddenly. When these barriers lifted, the organisms might have re-entered the broader oceanic system, creating sudden reappearances at odds with the surface record. This phenomenon, if true, could explain the repeated patterns of Lazarus returns among deep-sea lineages. But it also suggests something stranger, that the deep ocean may have isolated itself at intervals, operating according to its own rhythm. And yet, for all the chemical and biological evidence of upheaval, the deep ocean often shows astonishing resilience. Foraminifera living at abyssal depths after the Kelvasser crisis recovered more quickly than their surface counterparts. Some deepwater brachiopods exhibit minimal morphological change across extinction boundaries, as though insulated from broader environmental swings. In rare cases, deep marine conodonts appear to diversify immediately after crises in ways that feel almost opportunistic, as if responding to openings created by disruptions elsewhere. But these bursts of diversity, like so many other patterns in the abyss, appear suddenly. They do not trace gradual adaptive curves. They erupt into existence and fade into obscurity without warning. This tension between upheaval and stability, isolation and reemergence, creates an impression that the deep ocean did not simply endure ancient catastrophes. It moved through them, reshaping itself in ways that do not always leave their full story behind. The deep sea feels less like a passive environment and more like an active participant in Earth's cycles, absorbing shocks, releasing energy, and sheltering lineages that surface sediments record only faintly. And as the listener drifts through this world of pressure and quiet chemical churn, there comes a deeper, more philosophical echo beneath the scientific details. If the deep ocean held its own catastrophes, its own refuges, its own rhythms of collapse and rebirth, then how much of Earth's true biological history lies not in what we have found, but in what we have lost? How many ruptures occurred where the record is most fragile? How many stories dissolved into black shales and ghost layers before they could reach the surface? The answers hover just beyond reach, suspended in the deep like particles in cold, unmoving water. And from that suspended silence comes another unresolved question, pulling the listener toward the next descent. If the deep ocean shaped life through unseen upheavals, what else might it have shaped or obscured? Far down where the record grows dark and the pressure seals the past away. As the descent moves beyond the upheavals and the silent forces that reshaped ancient waters, the next layer opens with a different kind of unease, one born not from catastrophes or vanished strata, but from the organisms that seem to whisper from the deepest vents of Earth. It is here, around hydrothermal chimneys and the chemical wounds of the ocean floor, that the story grows older, stranger, and more resistant to conventional timelines. If earlier parts hinted that the abyss once followed its own rhythm, this portion begins to reveal that the oldest rhythms may not have belonged to sunlight-driven life at all. For decades, researchers believed that life diversified most rapidly in shallow seas. These were the places of light, warmth, and nutrients. But as deep-sea exploration expanded in the 20th century, a contradiction began to unfold. Quiet at first, then increasingly insistent. Organisms living around hydrothermal vents carried genetic signatures far older than expected. Bacteria feeding on sulfur and metals displayed biochemical pathways that seemed ancestral, not derived. Even today, entire groups of archaea found in these depths show lineages branching close to the base of the tree of life. They are not primitive. They are primordial, elegantly adapted to a world without sunlight. This creates a quiet rift in the accepted story of evolution. If life began in warm, shallow pools near volcanic shores, as many propose, why do the deepest ecosystems possess biochemical systems that appear closer to the origin? Why do vent communities have metabolic strategies that function without photosynthesis, without oxygen, without the energy sources typically assumed to shape early life? It raises the unsettling possibility that the deep ocean may be less a refuge of later adaptation and more a remnant of the earliest world, a world preserved under pressure, heat, and chemical gradients that mimic the conditions of the young Earth. Evidence supporting this possibility comes from the structure of hydrothermal vents themselves. Ancient chimney fossils, dating back nearly 3.5 billion years, preserve mineral layers whose patterns match modern vent deposits. These fossilized chimneys appear in rocks from the Barberton Greenstone Belt and the Pilbara region of Australia. Yet the organisms that once inhabited them remain elusive, leaving only chemical fingerprints, ratios of carbon isotopes, traces of sulfur-reducing life, and metallic biomarkers that suggest a thriving microbial community. The continuity between ancient and modern vents is clear, but the puzzle lies in what is missing. Intermediate forms, evolutionary transitions, or any indication that life moved gradually from shallower to deeper habitats. Instead, the record seems to show the opposite. Whenever ancient vents are examined, they resemble modern ones with startling fidelity. The basic architecture of vent ecosystems, tube worms, chemosynthetic bacteria, bivalves, seems to appear fully assembled in each era. And while the individual species differ, the community structure is eerily consistent, as if the vents preserved a template older than the surface world itself. Some researchers argue that vent life is conservative, driven by chemistry rather than ecology. But even this explanation does not fully address the persistence of primordial traits, nor does it explain why some vent organisms show evolutionary divergence from surface lineages that occurred millions of years before their shallow water relatives even existed. This implies a deep time separation so profound that the surface world may represent only one of several evolutionary experiments, rather than the central story. Then there is the question of genetic isolation. Many deep-sea vent species show extreme endemism, unique to a single ridge or basin, separated by thousands of miles and millions of years. Their genetic divergence suggests long periods of isolation, yet they often share ancestral traits with other vent communities across the globe. It is as if these organisms migrated during ancient periods of connection, periods not clearly recorded in the geologic or tectonic timeline. Some propose that mid-ocean ridges once formed continuous pathways linking distant basins. Others suggest that microbial mats or larval forms drifted across the deep ocean via unseen currents. But none of these ideas account for the precision of the genetic relationships or the age of the divergence events. One example stands out: the Alvanellidae family of Pompeii worms, which thrive in temperatures exceeding 80 degrees Celsius. Their closest relatives appear not in shallow waters, but in other deep basins, thousands of kilometers away. The molecular clock estimates for their divergence do not match known patterns of ridge formation. Instead, they point to older, more mysterious intervals, times when the deep ocean may have been more interconnected than the surface. This leads to a subtle, provocative idea that some researchers mention quietly. The deep ocean may have held networks of stability that outlasted surface ecosystems. When continents shifted, climates changed, and shallow seas rose or fell, the abyss may have continued its own lineage, uninterrupted. This would explain why vent organisms often appear unaffected by mass extinctions, why their lineages show continuity where others show rupture, and why their traits feel ancestral. But the mystery deepens further when one examines the chemical signatures of ancient vents. Isotopic studies have revealed anomalies in carbon and sulfur ratios that resemble modern chemosynthetic ecosystems. Yet these signatures appear in rocks predating the earliest widely accepted fossil evidence of complex life. Some researchers propose abiotic processes. Others argue for microbial activity. But the timing raises questions. Could life at vents have existed before the first shallow water organisms evolved? If so, how many stages of early evolution have been lost to subduction or metamorphism? The abyss, in this sense, might not simply preserve fragments of ancient life. It might preserve fragments of a world before the one recorded in shallow sediments. A world where early organisms thrived in a rhythm defined by chemical gradients rather than sunlight. And if this world preceded the surface story, then the conventional narrative of life's rise becomes a smaller chapter in a larger, more complex book. Yet even this possibility does not capture the full strangeness of the evidence. In several deep marine basins, microfossils have been recovered from rocks formed near subduction zones, places where oceanic crust is pulled into the mantle. Some of these microfossils contain organic structures that do not match known groups. A few resemble early eukaryotes. Others appear bacterial but with unusual cell wall chemistries. Their preservation suggests rapid burial under immense pressure, as if entire microbial communities were dragged downward before being fossilized. These remnants feel like accidental witnesses to an older ecosystem that has otherwise vanished. And then there is the quietest hint of all, the trace molecules discovered in serpentinized rocks, formed deep within the oceanic crust. These rocks sometimes contain hydrocarbons that resemble biological signatures, yet they form in environments too harsh for most known life. Some propose abiotic synthesis. Others whisper that perhaps the distinction between abiotic and biotic chemistry in these depths is narrower than we imagine. As the mind descends through these uncertainties, the listener is left with a quiet but persistent impression. The deep ocean may not just preserve ancient life, it may preserve ancient origins. It may hold the memory of a biosphere older than the biosphere we know, shaped not by sunlight and surface dynamics, but by pressure, heat, and chemical whispers rising from beneath the crust. And as the final thought forms, fragile and unresolved, it points to a deeper, untouched question, one that waits like a faint glow at the next depth. If the earliest world hid in the abyss, what else from that world might still be living there, unseen, in places where time moves differently, and the record shifts into silence? By now, the descent has carried the listener far beneath the familiar zones of ancient oceans, beyond the vanished ecosystems, the ghost layers, the deep time upheavals, and the primordial worlds around hydrothermal vents. What lies ahead is not darker, but stranger. The spaces where the fossil record becomes too clear. Places where preservation is almost unnaturally exquisite, as if time paused just long enough to capture the outline of creatures that should never have survived long enough to be remembered. These are the deep marine Lagerstätten, the exceptional preservation sites. But in the abyss they behave differently. They appear without precedent, vanish without successors, and offer scenes so vivid they feel like accidental windows into worlds that were not meant to remain visible. Most people know the famous shallow water sites. The Burgess Shale with its delicate limbs and gossamer tissues, Chengjiang with its early eyes and muscles suspended in shale like pressed memories. But fewer know the deep marine counterparts, sites where conditions briefly aligned to preserve life at depth in fragile detail. These deposits do not resemble the broad cosmopolitan ecosystems recorded in shallow settings. They feel claustrophobic, closed, like snapshots of small worlds sealed away by pressure and darkness. And much like the organisms themselves, the circumstances of their preservation are often inexplicable. Consider the Maison Creek-type deposits found in deeper water environments far from the coastal deltas that produce the classical sites. In these dark basins, concretions lock away soft-bodied organisms whose ancestors are unknown and whose descendants never reappear. Some of these fossils display anatomical details so crisp, muscle fibers, digestive tracts, bioluminescent organ impressions, that researchers have spent decades debating whether their preservation was the result of freak chemical conditions or something else entirely. But what troubles many is not the clarity. It is the absence of context. The surrounding strata show no signs of the biological richness that such organisms would require. They appear in numbers too small for ecosystems and too isolated to imply a thriving community. It is as if they were preserved not because they lived there in abundance, but because they happened to pass through a moment when the seafloor captured them by accident. Even more unusual are the deep Ordovician Lagerstätten of Morocco, preserved in sediments once thought to belong exclusively to calm continental margins. There, anatomically complex organisms appear far earlier than expected. Some have soft tissues seldom seen in shallow settings of the same age. Others reveal sensory structures that align more closely with later evolutionary stages. These fossils are not plentiful, but the few that exist present organisms at a level of complexity that does not match the surrounding record. Their presence feels like stolen pages from a deeper narrative, a narrative whose earlier chapters are missing. The problem is not simply that these fossils are detailed. It is that they are too detailed for environments that rarely preserve anything at all. Deep marine deposition typically destroys soft tissues, scatters skeletal remains, and buries organisms quickly under shifting mud. Yet in these rare windows, preservation seems almost selective. Only certain forms, certain species, certain fragments of the deep-sea world are captured. Others, sometimes far more abundant based on trace evidence, remain entirely absent. This selectivity cannot be fully explained by chemical gradients or sedimentation dynamics. Something about these windows feels curated, as though only specific kinds of life could pass through them. The Burgess Shale, too, contains hints of deep water influence. While often described as a shallow shelf community, its deposition occurred in a basin structure that plunged to depths capable of mixing with nutrient-poor, anoxic waters. Some of the organisms preserved there appear to have traits more consistent with deeper habitats: reduced pigmentation, specialized sensory structures, morphologies suited to dim or unstable lighting. These traits do not align perfectly with a shallow water ecosystem. They whisper of creatures moving between worlds, slipping in and out of invisible corridors where light dwindles and pressure rises. Soft-bodied preservation in such environments often involves rapid burial under mud flows, turbidity currents, or sudden chemical shifts. But the timing is uncanny. These events capture communities in transition, moments when species appear in layers where they do not belong. A trilobite adapted for deeper conditions appears alongside shallow-dwelling worms. A soft-bodied predator from darker waters is found near species known to prefer sunlight. These juxtapositions seem random at first, but their recurrence across multiple sites suggests a more complicated history, one where organisms moved between zones more fluidly than the fossil record implies. Some paleontologists propose seasonal migrations. Others attribute the mixtures to downslope transport. But neither explanation accounts for the consistent presence of deeply specialized forms in layers that should have excluded them. Nor do they explain the disappearance of these forms immediately after the events that preserved them. If these organisms participated regularly in such movements, why do they leave no trace in surrounding sediments? Why only in the precise moments when conditions capture their soft tissues? A more subtle mystery lies in the chemistry of these deposits. Many show evidence of unusual mineralization processes, rapid pyritization, phosphatization, or iron replacement that require fine-tuned conditions of decay, oxygen exposure, and microbial activity. Yet these processes seem to occur even when environmental proxies suggest the necessary conditions were unlikely. It raises the unsettling notion that exceptional preservation may reflect not just geological accidents, but intervals when the biological and chemical fabric of the ocean shifted abruptly, creating brief windows where life could be fossilized with unnatural clarity. Some researchers have noted that these windows often follow periods of environmental stress, minor anoxic pulses, volcanic disturbances, or shifts in ocean circulation. But the alignment is inconsistent. Some Lagerstätten appear at times of apparent stability, without any hint of the crises that typically generate anoxic conditions. Others appear shortly after disturbances too short-lived to explain widespread preservation. And still others coincide with events that seem to affect only the deep sea, with no surface counterpart. The deeper the listener descends into the evidence, the more these exceptional fossils begin to feel like fragments from a world that passed briefly into visibility before disappearing again. Not fragments of an alternative world. Nothing so dramatic, but fragments of an older, more complex history of the deep ocean. A history that did not always align with the surface narrative. A history preserved only in slivers, as if the ocean itself allowed brief glimpses before closing again over its secrets. And beneath this accumulation of strangely perfect fossils and strangely imperfect explanations lies a quieter unease. These deep marine Lagerstätten do not behave like continuous records. They behave like interruptions, moments when the ocean revealed something unintended. Moments where the boundaries between layers, the living, the dying, the sinking, blurred long enough to capture creatures that were not meant to linger. What those creatures represent is still unclear. Whether they are relics of old lineages, migrants from hidden refuges, or simply organisms caught in the wrong place at the right time. But their presence deepens the central question that has guided the descent from the first part to this one. Why does the ocean reveal its deepest secrets only in fragments? Why do the clearest windows open not into stable ecosystems, but into moments of transition? And what does the ocean hide in the vast stretches between these windows? Stretches where the sediment grows dull and the silence grows heavy. The answer is not here. It waits deeper, in places where predators once moved like shadows in a world without sun, and where the next layer of the mystery begins to unfold. Somewhere below the fossil windows that flicker open and close like brief lanterns in prehistory, a different presence begins to take shape. One that does not come from preserved tissues or delicate impressions, but from the shadows cast by ancient predators. As the descent continues, the listener finds themselves entering a realm where the deep ocean was not merely a refuge or a cradle of strange biochemical worlds, but a stage for creatures shaped by darkness itself. These predators do not announce themselves through abundance. They appear in fragments, scattered traces, silhouettes of jaws or fins or shells that hint at something formidable moving along the ocean floor long before the surface world imagined such shapes. And it is here, in the uncanny rise of these night predators, that another contradiction pulses through the record. The deeper the habitat, the more extreme the forms become, and the more unpredictable their evolutionary paths appear. In shallow waters, evolutionary trends tend toward gradual adaptation, incremental elaboration. But in the depths, both in the Paleozoic and Mesozoic worlds, gigantism, sensory specialization, and sudden morphological leaps seem to emerge without warning. It is as if the deep ocean, free from the constraints of light and surface dynamics, followed its own rules of ferocity. Ichthyosaurs offer one of the clearest examples. While most were fast-swimming predators of the open ocean, some early Triassic forms show adaptations for deeper hunting, enlarged scleral rings for dim vision, pressure-resistant rib structures, and skull proportions suited for ambush rather than pursuit. But these features appear abruptly, in fossils only a few million years after the extinction that ended the Permian. The surface world was still rebuilding itself. Ecosystems were fragile, and marine diversity had barely begun to recover. Yet in this moment of ecological fragility, deep-water ichthyosaurs were already specialized, as if they inherited abilities from ancestors that did not survive the extinction. Paleontologists debate this, cautiously noting that the fossil record is incomplete. But even within that caution lies the quiet acknowledgement that some traits arrive too early, too suddenly. Mosasaurs, too, reveal hints of the abyss. Though often imagined gliding beneath sunlit seas, several lineages show anatomical features adapted for deeper diving: reinforced ear structures, expanded thoracic cavities, and sensory organs that resemble those of modern deep-diving cetaceans. Some mosasaur fossils even show signs of pressure damage, bony pathologies aligned with rapid depth changes. And yet, their earliest forms lack these features entirely. The adaptations appear in isolated bursts within the Cretaceous, suggesting that certain lineages pushed into deeper habitats independently, then vanished again without leaving transitional forms. Ancient ammonites and belemnites add another layer to the puzzle. Many species evolved intricate chambered shells capable of withstanding high pressures. Some show stable isotope ratios indicating deep water living, far below the photic zone. And in several cases, their shells grow disproportionately large relative to shallow water relatives, a pattern associated with increased pressure and low temperatures. Yet the earliest deep-diving ammonites appear shortly after the end Triassic extinction, without the gradual development of pressure-resistant traits. The suddenness feels like a recurring echo, the deep repeating a familiar pattern, predators emerging fully prepared for conditions that should have required lengthy evolutionary preparation. Even earlier, in the Paleozoic, predators of the deep behaved in similarly elusive ways. Goniotites from the Devonian show suture patterns that suggest structural reinforcement for deep water pressures. Some were found alongside conodont elements adapted for low-light hunting. Jawed fish like Dunkleosteus, though often reconstructed as shallow-water giants, have isotopic signatures in some specimens that imply deeper foraging. And certain eurypterids, typically associated with coastal habitats, left behind impressions found surprisingly far from ancient shorelines. Locations once connected to deep basins. If this were a simple matter of ecological expansion, the fossil record would reflect it through transitional morphologies, gradual thickening of bones, progressive changes in sensory organs, incremental adjustments to buoyancy structures. Instead, what appears are abrupt entries and abrupt withdrawals, organisms that materialize in the deep already specialized, then vanish without leaving intermediate steps. This pattern becomes even more enigmatic when examining sensory adaptations. In multiple lineages, deep-sea predators develop oversized eyes or, conversely, reduced eyes optimized for low-light detection. But these features do not align with stable deep-sea conditions. They appear during periods of environmental instability, global cooling, volcanic activity, oceanic turnover events. How could predators evolve traits suited for darkness during times when deep ocean conditions were shifting unpredictably? The timing hints at ecosystems that were already structured for deep predation long before the surface world experienced the pressures that might select for such traits. The phenomenon of gigantism deepens the contradiction. Many deep-water predators, ichthyosaurs, certain sharks, giant ammonites, even some Devonian arthropods, grew to sizes disproportionate to their shallow relatives. While deep-sea gigantism is a recognized pattern today, its appearance in ancient oceans is often too early and too extreme to match predicted energy budgets. Some species seem almost overbuilt for their habitats. Others possess anatomical features that imply metabolic rates higher than those expected in cold, low-resource environments. This creates a paradox. Did the deep once harbor more abundant energy sources? Or were these predators shaped in environments that no longer exist? Modern analogies fall short. Today's deep-sea predators rely on stable but sparse ecosystems. But the ancient predators recorded in deep water deposits suggest bursts of opportunity, times when prey was abundant, or when the deep offered refuges of stability while surface ecosystems collapsed. Yet the fossil evidence supporting such refuges is inconsistent and incomplete, leaving a sense that the deep was both sanctuary and battleground, its conditions shifting in ways that did not always leave a footprint in the surrounding rock. Another layer of strangeness emerges in the patterns of disappearance. Many deep-sea predators vanish not during global extinction events, but immediately before them, as if responding to changes the surface world had not yet experienced. Others disappear long after surface ecosystems have collapsed, as if lagging behind or moving in response to delayed environmental signals. These mismatched timings suggest that the deep ocean operated on cycles not visible in surface proxies, cycles driven by temperature gradients, chemical fluxes, or tectonic shifts that never reach the light. No single explanation resolves the contradictions. Some propose migratory behavior, suggesting these predators moved between depths in ways that obscure their evolutionary origins. Others propose hidden basins or refuges now lost to subduction. A few suggest more radical ideas, that deep ocean ecosystems once followed rhythms unlike those of the surface, rhythms governed by chemical pulses, hydrothermal surges, or isolated energy sources long gone. But whatever the cause, the impression remains. The deeper we descend into the prehistoric seas, the more the predators resemble echoes from a world with its own internal logic. A world where life responded to pressures, literal and metaphorical, that are difficult to reconstruct. A world that seems to have produced complexity not as a gradual climb, but as a sudden emergence, like shadows rising from below. And as these predators fade into the darkness of extinct basins, leaving only fragments of jaws or ribs or shells behind, the descent moves into a quieter realization. The deep did not merely hide life, it shaped it in ways that defy the surface narrative. It may have held threats, cycles, and opportunities invisible to the sunlight world. That realization leaves a final question for this layer, one that opens the next descent. If the deep could produce such predators without leaving a continuous record, what else might have risen and disappeared in those unlit spaces? Unnoticed by the history written in stone, the descent now approaches a region of the story where silence is heavier than pressure, where the ocean seems to hold its breath in the aftermath of calamity. If the earlier layers revealed predators shaped for darkness, this one reveals what happened after the world above them collapsed. It is a part of the tale where extinction arrives not as a dramatic crash, but as a slow, smothering hush. A hush that descended over the oceans after the greatest impacts and upheavals in Earth's history. Yet within this hush, the deep behaved in a way that refuses to match the surface story. The surface world shattered, but the abyss whispered back its own quiet logic. The Chicxulub impact, which ended the age of the dinosaurs, is often told as a tale of fiery skies, worldwide darkness, and collapsing food chains. Photosynthetic life faltered, marine plankton dwindled, and shallow water ecosystems spiraled into chaos. But something unexpected happens when one looks at the deep marine record. In certain places, It barely flinches. Some foraminifera, tiny shelled organisms living at tremendous depths, recovered faster than their surface-dwelling relatives. In other places, deep-sea sediments show patterns of survival that seem impossible given the global devastation above. The deep should have been starved of organic input, yet some communities persisted, even diversified, when logic suggests they should have vanished. Worse for the neat version of the story, some deep-water organisms disappear before the impact layer even forms. Their extinction precedes the asteroid's arrival by tens of thousands of years, as if responding to a disturbance that has left no surface trace. Others vanish after a significant lag, out of sync with climatological proxies and global geochemical signals. These misalignments, scattered across various basins, hint at a deeper complexity, a sense that the deep ocean followed a different script in the wake of catastrophe. Then, there is the matter of the clay layer. For many shallow and mid-depth sites, the impact is marked by a thin but unmistakable seam, rich in iridium and shocked minerals. But in the deepest cores, this seam behaves strangely. In some locations, it is thickened, its contents stretched like a smear. In others, it appears as multiple thin layers separated by subtle chemical differences, as though deposition occurred in pulses rather than a single event. A few cores reveal microfossils rearranged in odd patterns, some crushed, others aligned as if transported by deep currents that surged unusually fast. Researchers attribute these distortions to turbidity flows or post-depositional effects. But the anomalous precision of certain features, sharp gradations, directional sorting, repeated microlayers, feels like something more deliberate, more structured. One of the most perplexing findings comes from the benthic foraminiferal record. Deep-sea benthic forams should have suffered immensely from the collapse of surface productivity. Yet several lineages show continuity across the boundary. A few even show early signs of recovery before shallow water species begin to rebound. This inversion of expected patterns raises a troubling question. What energy sources sustain these organisms when the entire planet's surface ecosystem collapsed? Some propose detrital rain from dying surface organisms, but this would have been brief and insufficient for long-term survival. Others suggest that deep-sea microbial activity surged, providing alternative carbon pathways. But these explanations are provisional, stitched together to cover a gap in understanding that still feels too wide. The more carefully scientists examine these deep boundaries, the more contradictions arise. For instance, some deep basins contain rare fossils of creatures that seem to reappear after the extinction, with no clear lineage connecting them to post-impact species. They feel like relics, survivors from older worlds that resurfaced only when conditions allowed. A few deep-water ammonite and belemnite lineages persist beyond their expected extinction windows, their isotopic signatures suggesting they inhabited zones far removed from surface instability. It is as if the deep momentarily sheltered lost worlds, allowing them a brief existence before they faded again. Another layer of mystery appears in the geochemistry of post-extinction sediments. Certain deep cores show spikes in trace metals and isotopic ratios that imply hydrothermal activity surged shortly after the impact. It is almost as though the planet responded from within, vents pulsing with heat, minerals rising from basaltic wounds, creating localized hot zones that temporarily fostered new ecosystems. Some researchers wonder whether these hydrothermal surges helped jumpstart recovery in the deep. Others consider whether the impact itself triggered tectonic changes that awakened long-dormant systems. But even these considerations do not resolve the timing gaps, the mismatched recoveries, or the occasional appearances of species that seem to have survived in isolation. These strange survivors become even more enigmatic when one studies radiolarian and diatom assemblages. In a handful of deep marine sequences, certain lineages of radiolarians, microorganisms that build delicate silica skeletons, exhibit abrupt diversification after the extinction, as if responding to an opportunity. But these radiolarians have no clear precursors in the immediate layers below. Their earlier forms are missing, the transition erased or hidden. It is reminiscent of a pattern observed in the Paleozoic, organisms appearing too suddenly, too structured, as if stepping out of silence already prepared. This impression stretches even further when the listener considers the bloom peaks, intervals where deep water life recovers far faster than shallow ecosystems. Some deep-sea organisms reach pre-extinction diversity within a few tens of thousands of years, while surface communities take hundreds of thousands or even millions. This difference is not merely surprising. It suggests that deep ecosystems did not depend solely on surface productivity. Something inside the deep, chemical reservoirs, microbial networks, unknown refuges, seemed to cushion the blow, buffering the abyss against planetary trauma. Yet the deep was not unaffected. In certain basins, sediments record long periods of stagnation, interrupted by sudden pulses of oxygenation. In others, current patterns shifted dramatically, redistributing nutrients in ways that remain poorly understood. And in some places, entire communities disappear abruptly, with no corresponding change recorded above. These disappearances feel almost like the closing of hidden doors. Doors that opened briefly during catastrophe, then shut as the ocean restabilized. The deeper this contradiction grows, the more the entire event begins to resemble a double-exposed photograph. The well-known image of global collapse layered atop a faint, almost invisible image of something else, something moving quietly in the abyss. The two pictures do not fully align. They create shadows and gaps, spaces where the listener senses an older logic running beneath the visible record. And as the mind descends further into this twilight of impacts and resurgences, a final realization begins to settle in. The deep ocean does not simply survive extinction. It metabolizes it. It reshapes it into something unrecognizable to the surface world. And in doing so, it hints that the history we read in shallow waters is only one version of events. The abyss may hold others, versions shaped by chemical cycles, microbial symphonies, and forces that unfold beyond the reach of sunlight. What those hidden versions reveal still waits below, in layers where not even catastrophe could erase the traces completely. And from that waiting quiet emerges another unresolved question, soft but persistent. If the deep ocean could rewrite extinction, what other stories has it rewritten that the surface world never knew to look for? Somewhere beyond the quiet aftershocks of ancient cataclysms, the descent crosses into a region of the prehistoric ocean that feels less like a place and more like a forgotten authorship. If the earlier layers revealed predators, upheavals, and vanished ecosystems, this one reveals something gentler, but far stranger. The architects of the ocean itself, not the large, impressive organisms that dominate museum halls, but the tiny, persistent builders whose work shaped entire worlds, and yet whose presence in the fossil record is faint, fragmented, or disturbingly absent. In this quiet part of the story, the listener drifts into the realm of planktonic engineers, microbial weavers, and chemical scribes whose traces hint at grand designs they left in water, not stone. These organisms, the acritarchs, the early plankton, the reef builders, the microbial giants of the Proterozoic, form the invisible backbone of marine history. Without them, the great predators of the deep would never have evolved. Without them, oxygen would never have risen. Without them, the ocean would not have become a place where life could bloom through epochs of instability. And yet, despite their importance, they often seem to vanish at the very moments their influence is most needed. Their story feels less like a chapter written in sediment and more like a fleeting breath across the surface of time. Take the acritarchs, for example. Enigmatic microfossils, some simple spheres, others elaborate structures that look almost decorative. They appear across Paleozoic strata, but their diversity and complexity spike at odd intervals, often without obvious causes. In some deep marine deposits, acritarch species appear suddenly, implying blooms of productivity. But these blooms leave no corresponding trace in shallow waters. It is as if certain planktonic worlds existed only in the abyss, beyond the reach of sunlight or conventional ecology. And just as abruptly as they appear, they vanish, leaving only empty gaps in the record. Some researchers attribute these fluctuations to changes in ocean chemistry. Others propose hidden currents or deep nutrient cycles. But the pattern remains: bursts of complexity in places where complexity should not thrive. Even more puzzling is the silence surrounding ancient microbial mats, the soft, gelatinous worlds that once carpeted the seafloor. These mats produced oxygen, shaped carbon cycles, altered sediment chemistry, and may have influenced the earliest evolutionary experiments. Yet in the deep sea, where such mats should have thrived for millions of years, the fossil evidence is scarce or highly ambiguous. Some laminated patterns hint at their presence, but the details are washed away. The deeper the layer, the more these microbial engineers dissolve into abstraction, as though the ocean allowed their influence to remain, but not their identity. They feel like authors whose handwriting has been wiped from the page. Reef systems reveal a similar contradiction. Early reef builders, stromatoporoids, tabulate corals, microbial consortia, constructed massive structures in the Devonian. They transformed coastlines, altered ocean chemistry, and created habitats for countless other organisms. But in deeper waters, where reef fragments occasionally appear, the story grows confused. Some deep water reefs show sudden expansions during periods of surface decline. Others collapse inexplicably, without sedimentological markers to explain their fate. Isotopic data from these structures sometimes suggest chemical conditions incompatible with known environmental settings. And when reef-building organisms reappear after extinction events, they often do so in deep-water contexts before migrating back to shallow seas. This reversal, deep first, shallow later, echoes the same pattern seen in predators and vent organisms. It hints at a hidden continuity beneath the visible world. But perhaps the most enigmatic of these architects are the tiny planktonic organisms whose shells form the ocean's rain of skeletons. The slow, steady drift of calcium carbonate particles that built chalk, limestone, and deep-sea ooze. Coccolithophores, foraminifera, and radiolarians played central roles in carbon cycling, but their early history is fragmented. Some deep marine sequences show their sudden appearance in places too cold or too nutrient-poor for them to have originated. Their earliest forms often possess complex skeletal structures, as though they bypassed primitive stages entirely. And in multiple basins, there are intervals, sometimes tens of millions of years long, where shallow-water plankton disappear from the record, while deep-water communities remain stable or even flourish. How could plankton, the quintessential surface organisms, thrive below the reach of sunlight? How could they diversify in darkness? Some propose sinking nutrient streams or chemolithotrophic metabolisms. Others suggest something more enigmatic, that deep ocean planktonic systems evolved along a different path than their surface counterparts. A particularly haunting example lies in the strange case of the late Proterozoic. During this era, before the rise of complex animals, the ocean's microbial systems underwent profound changes. Stromatolite reefs collapsed worldwide, replaced by mysterious sea-floor snow. Organic flocks, microbial colonies, and mineral-coated particles drifting through the deep. Some of these particles fossilized in unusual ways, forming structures that resemble spores, cysts, or resting stages of organisms that have no clear modern equivalent. Their chemistry suggests metabolic pathways distinct from known groups. Their distribution implies ecosystems that moved independently of surface conditions. And yet, after a few tens of millions of years, they disappear with almost no trace, replaced by entirely different communities that emerge without continuity. This uncanny discontinuity repeats across geological eras. Ancient reef systems appear fully formed, vanish, reappear in new contexts, and then disappear again. Microbial ecosystems that should have persisted for millions of years suddenly retreat or shift into environments where they leave no sedimentary record. Planktonic builders emerge in deep waters before colonizing the surface world. None of these patterns align neatly with environmental reconstructions or tectonic frameworks. They suggest that the architects of oceanic ecosystems operated within cycles obscured from our view, cycles that left chemical signatures but erased the organisms themselves. What makes this part of the descent so quietly unsettling is the realization that much of Earth's early evolution was dictated not by the grand, visible creatures, but by these invisible engineers. They controlled the oxygen that predators breathed, the nutrients that reefs consumed, the carbon that shaped climates. Yet their own history is patchy, fragmented, or submerged beneath layers of time erased by pressure and chemistry. It is as if the ocean hid the identities of its true builders, leaving only the architecture behind. And this leads to an even deeper reflection. If the structures remain but the builders vanish, what does that imply about the continuity of life in the abyss? Did entire worlds of microbial and planktonic architects rise and fall beyond our ability to detect? Did they leave behind only narrow chemical hints, faint shadows in carbonate curves or sulfur ratios? And how many of these ancient architects might still exist today in forms so altered by time that we would not recognize them? The descent does not answer these questions. It merely draws the listener toward the next depth, where the ocean becomes older than fossils, older than sediment, older even than the conventions of time that shape the layers above. As the descent continues, and the listener drifts into the regions where the ocean becomes more ancient than the fossils it holds, there is a shift in atmosphere, subtle but unmistakable. The world below no longer feels like a sequence of eras or ecosystems, but something more untethered, as though the rules of chronology begin to soften beneath the weight of pressure. Here, in the deepest trenches and subduction-carved abysses, time behaves differently. Not metaphorically, but physically, bent, warped, and folded by geological forces so immense that even the record of life itself becomes distorted. And in these shifting depths, strange anomalies appear. Chemical signatures older than the rocks that house them, microfossils preserved in places they should never be, and traces of life that seem to defy the straightforward direction of evolution. The deepest trenches of the world, Mariana, Kermadec, Tonga, Java, are not simply depressions in the ocean floor. They are places where the crust bends into angles that distort both matter and meaning. Modern studies show that pressure here compresses sediments into forms that obscure their age, while temperature gradients transform organic molecules at unpredictable rates. This should erase history. And yet, paradoxically, Some of the oldest biological signatures have been found in precisely these environments. In serpentinized rocks pulled up from subduction zones, geochemists have detected hydrocarbons with isotopic ratios resembling biological origin, compounds that should not survive the metamorphic conditions that created these rocks. Some argue that the signatures are abiotic, formed by chemical reduction of carbonates. Others insist that the patterns match microbial life too closely to dismiss. But the deeper one examines the data, the more the distinction between chemistry and biology seems to blur. There are other puzzles. In some of the deepest cores drilled into forearc basins, microfossils appear in layers far younger than their species should allow. Radiolarians that vanished in one era, reappearing millions of years later. Or siliceous spicules showing morphologies known from earlier worlds. Some researchers propose reworking. Fossils eroded from older sediments and transported into younger layers. But the microstructures of these fossils, uncrushed, undamaged, perfectly preserved, do not match the chaotic signatures of reworked debris. Instead, they appear almost as if lifted intact from a different time and sealed in new sediment. A few papers examine this cautiously, noting the strange integrity of the specimens. But most avoid deeper speculation, leaving the questions to hover unanswered. The same ambiguity appears in deep carbon measurements. In certain trenches, the carbon isotopic composition of sediment layers suggests biological activity predating the formation of the rocks that house them. Some propose that fluids circulating through subducted slabs carry ancient signatures upward, imprinting old carbon onto new layers. But even that does not fully explain the presence of biomolecules that degrade quickly under normal geological conditions, yet remain stable here. It is as though time slows, not metaphorically, but chemically. Under the crushing loads of the deep, subduction zones also create one of the strangest puzzles in the study of ancient life. The preservation of microfossils in rocks that experience pressures and temperatures normally sufficient to erase all traces of organic matter. Yet in certain ultra-deep metamorphic complexes, researchers have found the faint impressions of microbial filaments preserved in graphite layers that should have recrystallized beyond recognition. These impressions are not detailed enough to identify species, but they are too structured, too regular, too biological to dismiss. The rocks are impossibly old, older than many surface fossils, and yet the structures appear younger. Or perhaps it is the opposite. The structures are older than the rocks, remnants of life from worlds that existed before the sediments transformed into stone. This inversion of age, the idea that some biological traces may be older than the rocks themselves, creates a quiet, lingering dissonance. It suggests that deep ocean processes fold time upon itself, preserving fragments of earlier epochs in newer materials. Some geologists have described subduction zones as memory engines, recycling the crust, but occasionally leaving imprints from deeper pasts. If so, then the deepest ocean does not document history. It distills it, blending layers of time in ways that surface sediments cannot record. Evidence for this temporal distortion also appears in the unusual mineral assemblages of the Hadal zones. Certain authigenic minerals form at pressures so extreme that their chemical pathways differ from anything found above. These minerals sometimes trap organic molecules that seem ancient not merely in age, but in character. Molecules with structures resembling those from pre-oxygen worlds. Some speculate that these molecules derive from microbes thriving in deep crustal habitats long isolated from the surface. Others suggest that the mineral matrices simply preserve old chemical patterns by accident. But there remains a persistent whisper in the data that some biochemical signatures may belong to archaic lineages still existing in hidden pockets of the deep or trapped between subducting layers. Even modern microbial studies deepen this impression. The deepest sediments sampled, some more than 100 million years old, contain living microbes whose metabolic rates are so slow that individual cells might persist for centuries or millennia. These organisms consume trace molecules in environments where time stretches beyond biological rhythms. Their genomes show peculiar traits, ancient metabolic pathways, enzymes that resemble ancestral forms, and genes adapted for extreme longevity. Some scientists call them zombie microbes, not because they are dead, but because they live on timescales humans cannot grasp. If such organisms exist today, what forms might have evolved or persisted in ancient trenches long before the fossil record began? The deeper the descent goes, the more the ocean's oldest layers begin to feel like a realm, not governed by the same chronological constraints that shape shallow history. Here, the idea of earlier and later dissolves. The boundaries between epochs blur under pressure. Chemical reactions slow or reverse. Biological traces move unpredictably through rock, and the organisms themselves evolve in rhythms that leave no clean record. This is not a supernatural mystery. It is a geological one, an interplay of pressure, heat, chemistry, and time so complex that the deepest ocean becomes an archive written in overlapping scripts. But even in its natural explanation, the unease remains, because it implies that our reconstruction of ancient life may be fundamentally incomplete. We see only the layers preserved in ordinary sediments. We do not see the layers folded, erased, recycled, or preserved as chemical ghosts deep beneath the crust. And as this thought settles, another begins to surface, quiet and unresolved. If the deepest trenches hold traces older than themselves, if time bends under pressure and leaves its imprints in unpredictable ways, then what hidden histories lie beneath even these? What earlier oceans, earlier worlds, earlier biospheres remain sealed in the parts of the Earth no drill has reached? The answer remains submerged in the crushing quiet of the Hadal depths, waiting in a darkness where memory itself changes shape. At the deepest point of the descent, where the ocean floor folds into trenches so narrow they seem like incisions carved into the crust, the story loses its shape. Not because it ends, but because it meets something older than narrative itself. A kind of quiet pressure that erases beginnings, smooths endings, and leaves only suggestion where certainty once stood. After moving through vanished ecosystems, ghost layers, impossible fossils, ancient predators, unseen architects, and distortions of time, the listener arrives at a final layer where the ocean does not reveal anything new. Instead, it reveals the outline of an absence, a space where the record thins into silence, and even the silence feels intentional. This deepest region is not marked by creatures or sediments or chemical trails. It is marked by the limits of knowledge. Here, the ocean becomes a boundary, the threshold beyond which the story of life fades not because it is finished, but because the medium that once held it has dissolved. The pressure collapses evidence before it forms. The chemistry erases clues as soon as they appear. And yet, paradoxically, this erasure leaves a shape behind, like a shadow cast by something that is no longer there. Some researchers call this the deep time barrier. Others describe it more poetically, the ocean's memory horizon. It is the depth at which records no longer behave like records. Rocks metamorphose, sediments compact into unrecognizable forms, organisms become chemical ghosts, and the patterns that once guided interpretations lose their continuity. What remains feels less like the past and more like the residue of something that has passed beyond the reach of reconstruction. In this place, Every question asked of the ocean becomes inverted. Instead of asking why a lineage appeared too early, one begins to ask why the deep ocean has preserved anything at all. Instead of wondering why the record of predators or plankton or microbial architects is incomplete, one wonders whether completeness was ever possible. Instead of searching for the origins of a trait or a lineage, one considers whether origins themselves are a surface world concept, something that dissolves under pressure, replaced by cycles without beginnings. As the listener drifts deeper into this thought, a realization begins to take form. The ocean is not lying. It is not hiding a secret timeline, or a lost biosphere, or an erased chapter. It is simply behaving the way it always has, recording what it can, dissolving what it must, and letting the rest sink into places where no sediment can reach. The gaps are not conspiracies. They are properties of matter. But knowing this does not reduce the mystery. If anything, it deepens it, because it implies that much of Earth's true biological history may lie not in what survived, but in what could never survive long enough to be preserved. This final layer of the descent is defined by that tension, the boundless magnitude of what once existed, and the tiny fraction that remains visible. The prehistoric ocean was vast enough to host entire ecologies that left no fossils, entire evolutionary experiments that vanished without leaving even a chemical trace. Some lineages may have lived and died in deep basins sealed by geological events. Others may have thrived near hydrothermal systems that left only ambiguous mineral residues. Still others may have persisted for long stretches of time, but left no shells, no bones, no hard structures that could outlast their own decay. Scientists occasionally glimpse hints of such invisible worlds, a genetic lineage that seems older than its fossil representatives, a chemical signature that appears too early or too late, a microfossil trapped in a place it should not exist. But these glimpses are like seeing the reflection of a distant fire on water. You know something is burning, but you cannot see the flame. This inability to see the full picture does not weaken the story. It strengthens it, reshaping it into something more humbling. The deep ocean becomes not a void but a mirror, reflecting the limits of human understanding. History at these depths is not a linear sequence, but a mosaic of fragments, scattered pieces from which only faint outlines can be formed. And every time a new fragment is discovered, it creates not clarity, but new complexity, another question layered atop the last. And beneath all of this, beneath the fragments and the uncertainties, lies the quiet awareness that the ocean may not be a passive archive at all. It may be an active force, shaping what is remembered and what is lost. Each layer of pressure, each chemical gradient, each overturn or volcanic surge may choose what survives. Not consciously, of course, but through the relentless consequences of physics. And in that sense, the ocean does not simply hold the past. It curates it. What then remains for the listener at this depth? Not answers, not conclusions, but something gentler and more haunting, a sense that the deeper one goes into prehistory, the more the familiar narrative dissolves into silence. The prehistoric ocean does not reveal a single secret. It reveals the vastness of what we do not know and what we were never meant to know completely. Perhaps this is the final lesson of the deep, that mysteries do not depend on hidden truths, but on the spaces where truth cannot survive. That life's history is not a complete tapestry, but a scattered constellation of lights, some bright, some faint, many forever lost beyond the horizon of pressure and time. And as the last traces of the abyss settle around the listener, closing in like soft sediment, the story ends not with resolution, but with a lingering suggestion that for all the fossils collected, all the cores drilled, all the sediments analyzed, The deepest places of Earth still hold stories older than memory, older than stone, older than time itself. Stories that drift just beyond reach, waiting in a darkness where knowledge sinks and silence endures. And perhaps that is the real reason the prehistoric ocean grows creepier the deeper one goes. Not because of what lived there, but because of what still lives in the spaces we cannot illuminate, what remains there, unseen. What persists in the folds of pressure where history dissolves? The descent leaves these questions open, like faint lights shimmering at the edge of the abyss, glowing softly before fading into the dark.